First, let me introduce Peter Lorre, CEO of Chronicle Software. Peter founded Chronicle in 2013 as he saw great demand for low-latency Java within the electronic trading community. During the past 7 years, Peter has been pivotal in growing Chronicle Software to become a trusted partner to many global Tier 1 banks and hedge funds. In addition, Chronicle open source software is downloaded over 17 million times per year and is used across multiple industries ranging from payments, biometric research, and even gaming consoles. The business has now grown to over 3 million per year turnover, with revenue growth in 2020 set to increase by over 30%. Prior to this, Peter held many senior consultancy positions for global financial institutions, including RBS, Barclays, UBS, and Reuters. Peter is a Java champion and one of the global leading experts in Java development, with the most answers on Stack Overflow. Peter has driven the use of Java in low latency, opening up the skills and capabilities required to build the most demanding app, and he continues to research and develop innovative ways to utilize Java within low latency microservices architecture. The format today will be a presentation followed by a Q&A. If you have any questions during the presentation, please submit them via a Q&A feature in Zoom, and Peter will answer them at the end. Over to you, Peter.
Thank you. Today we'll be looking at the design and testing of low latency microservices. By low latency, we typically look to add only about 10 to 100 microseconds, including business logic, and of course we want the infrastructure to be a very small portion of that. Another thing to consider is that the sort of systems we were working on, they're targeting only about 1% utilization, sometimes far less. The reason for this is that 1% utilization means that 1% of the time when a new event comes in, you're still dealing with the previous event, which means that even a 1% utilization is hurting your worst 1 in 100 or your 99th percentile. So a lot of traditional systems might expect to have much higher utilizations, but to keep latencies low, we're actually looking to have a very low utilization, but it also means intrinsically we have a high capacity headroom to handle bursts of activity. So the sort of products that we're talking about today that are relevant to today's talk are mostly open source, and in fact the demo I'm about to show is also open source, and it sits around Chronicle Q, and there's the Chronicle Services framework which helps build these microservices, but it's all built on Apache 2 licensed frameworks, and they in turn can be built on top of Docker. When we've benchmarked our products working in Docker versus raw machines, we can get very similar performance. In fact, the difference is not easy to show on a graph because it's pretty much the same, slightly lower performance, but not anything to be too concerned about. So the architecture that we approach is generally called Lambda Architecture, or in fact it's a component of Lambda Architecture which focuses on functions where you've got an ever-growing event source coming in, and function is applied, and that produces another event source which can be consumed by other processes. The more idealized function where it is stateless is easiest to test, but has limited application. So what we do is we have a variation of that where we have what is effectively a stateful function, but the difference is that the state there the function is essentially the result of every event it's ever seen, not just the latest event. But obviously replaying every event each time is not performant. So instead, a state or cache is maintained, which allows it to simulate this but still process each event as it comes in. So you get the performance of the top example, but you have the power of having what is notionally what is effectively has state, but has the properties of an immutable function all the same. Now these can be combined together, and typically the non-stateful functions tend to exist on gateways in and out of the system. So in this case, we've got fixed messages coming in. They get normalized into internal format. That normalization doesn't have to be stateful, so that can be kept really simple and stable, and generally doesn't need to be upgraded or restarted. A lot of the core logic is in the control system or control systems in the middle. They maintain some state because, like I said, replaying every message for every new message is not efficient, but it can still is a very deterministic replayable system. And in the purpose of testing this control system, which is in the middle, the only thing you need is the inbound messages. So significantly, you don't need access to a database, you don't need access to any resource that's from production. As long as you have the inbound messages, which are just some files in a queue, you can copy them, replay them, debug the code, work out what's wrong, and once you've fixed it, replay it again and have confidence you really have fixed it, and you have a reproducible, highly testable, highly performant system. You're not dependent on any network I/O or database queries, locking, delays of any kind. Also, the way the components are written and the way the infrastructure is written is that they produce very low garbage. So we don't see significant pauses either. And in fact, we tend to favor just using the parallel collector because it's very simple and has a deterministic GC time. So you don't need GCs when the Eden space fills up. So if we make a large Eden space and we produce very little garbage, we can run for an entire day without a minor collection. Part of the reason we can use these very large event sources is that this space is getting cheaper, so it's getting more performant and cheaper. These drives, as an example, they can handle in the order of 1 to 3 gigabytes a second write speed. They are very cheap, even though they're enterprise grade, and they're also very dense. So you can have a 1U server with half a petabyte, and for a very reasonable cost. And not that any of our clients have ever needed a half a petabyte, but for this kind of storage. But should you have the need, there's more than enough capacity. Generally, our clients have in the range of 1, 2, or 4 terabytes, which is sufficient to store recent events and then have it periodically archived, compressed and archived, or deleted. Another key factor that's driving our design is the assumption that the cores are getting cheaper and more readily available. You can have now a desktop server, a box with 64 cores for well under 10 grand, and that obviously gives you both an opportunity to use more cores, but also a challenge of how do we use those cores efficiently and effectively. So, as Moore's law continues, we will see higher core counts in retail, but even banks, which tend to be conservative and take more reliable systems rather than leading edge, they will see servers with this kind of core count being quite common. So now I'm going to switch into a demo, which is open source. You can run the demo yourself, but I'll go through some coding examples. The benchmark, which is also in there, shows a number of alternative ways of doing the serialization to reduce the overhead. For simplicity's sake, we just encourage using what we call self-describing marshables. which have the benefit of being the easiest to use, can support schema changes quite readily, adding and removing fields, changing their order, changing data types are all supported. So that helps with development. But you've also got the option that, particularly if you've got a large DTO or a very common one, and you believe it's pretty stable, you can improve its efficiency by making it more and more compact without having to make significant code changes. So we'll go into the example. So if we start with, so this is the repository, which is in the link. We will be sharing the presentation to everyone who's registered. And there are other examples, but this particular example is called Order Processor, and it illustrates.
Are you going to go into the code, because we can only see the chart at the moment?
I've switched tabs. Maybe let me try changing the sharing.
That's better. I can see that now.
Okay. So this is the repository, which has some examples. Today we're going to look at this order processor example. It shows how our projects are generally laid out, and a lot of the design is around interfaces. So an interface is used to define all the events that can come into a system. It also has another interface to define all the events that can come out of a system. And this combination allows us to check in code at compile time a lot of the integration issues that may happen between upstream and downstream services. However, it doesn't have to follow these strictly. It has, at runtime, the versions can be a little bit inconsistent and everything will still work. It doesn't have to be as strict as this at runtime, but this will give you assistance to ensure that your services match, that you're not trying to publish an event from one service that the downstream service doesn't know what to do with or ignores. So it is fairly straightforward to write an implementation. The implementation itself implements the inbound interface. So for each possible event coming in, which has its own DTO, you have a method which implements what happens when that event occurs. There's two events coming in, and in return, an implementation of the output interface is provided, so you can say, well, these are all the events that come out. So in this example, a new order single comes in, and essentially it just rejects every new order single coming in, sending out an execution report. So let's see what the tests look like. So the test harness is data-driven, so it can be code-driven. Obviously, it's very easy to write a test to just create one of these components, call methods on it directly, and then have some expected results. But we favor using data-driven tests because this has some advantages when it comes to, particularly to do with maintainability, which I will show you in a moment. And also how it tells you its error handling is, again, a lot cleaner. So in this case, let's have a look at a new order single. IntelliJ allows us to click on a string and show us a directory and resources that matches that string. So we can quickly see where the test is. And there's two files, which is the inbound event. So this is the event that comes in. So this matches the method name that gets called. So for each method on your component, you can just put an event. Because the type of that method is known, it knows to cast this or to deserialize this data as a new order single DTO, and it goes through and sets all these fields. So you'll notice that there's a microsecond date timestamp and there's a number of strings. Now, if we have a look at the DTO, though, as you probably know, using strings and deep timestamps can be expensive, both from a GC point of view and a memory overhead point of view. So we have a couple of techniques to mitigate that. We support conversion formats. So internally, whenever the messages are sent in binary or stored in memory, in reality, those fields are longs. However, there's a number of converters that allow you to convert it into text. So the timestamp is a fairly obvious choice. One, it's just it takes a microsecond timestamp, converts into a long, and vice versa whenever text is dealt with. For the purposes of strings, one of the ones I favor is a base 85. The reason for base 85 is that it's the largest base that supports storing 5 characters in a 32-bit integer or 10 characters in a 64-bit integer. So we take the 85 most common ASCII characters, and that allows us to have a string of most possible characters and symbols, ASCII, and of 0 to 10 characters long. So it allows us to play with strings in terms of testing and data-driven test. So it's all nice and readable, but internally we're just using integers, which makes it more efficient. So let's try running one of these tests, and we'll see how things such as maintainability are supported. So obviously now the test should pass, as it does. But let's break the test and see how easy it is to detect what the issue is. So I'm just going to add an extra digit into here, into the price. Okay. Now, the way a lot of tests are written, it will tell you that the test has failed, but it won't be obvious why did it fail, and how easily can I fix it. So as you can see, the test has failed, but we can also see quite clearly that even for a fairly large, complex data set, and for one client we had a megabyte of expected result, but you could very quickly see which fields, which values are incorrect. Not only that, we can also fix it very easily. So we can take the expected result, since we know that that is actually correct, and just overwrite it, and now the test passes. So a common problem with the DTOs is adding and maintaining the data structure. So let's try adding a field to abstract event. Now, abstract event is a super type of all the other types. So if you have a quick look at the order single, you can see it has the standard types of abstract event, which is we'll see in a moment, but it also has symbol, transaction time. Both of these are encoded, and some price and quantity inside, some enums and a string. But let's go into abstract event and add a new field. For simplicity, I'll make it a string. Again, it could probably make it a long, but for now we won't. Use IntelliJ to add it, the getters and setters, although because this is a parent class, we're using a trick to maintain its type. So that just needs to be hard-coded for now. Now, if we run the test, let's just run both tests, we expect them to fail, because now we have a new field, but we haven't changed any code, any other code. And as we can see, the test does fail. We've got a count, but it's null. It's not set to anything. So let's add it to the input of our results. We add it to the order single. We go to the implementation. We then say on the output, so we're just going to copy the account from the new order single, which is what we added to the input, and we will expect to see it on the output. Okay, so we can see the test fails as expected, because now we're actually getting an account field, but we didn't update the expected result. So let's add that to the expected result. We've added the field that we just added with its value to the expected result, and we'll see that now new order single is passing. So let's try debugging this. What does that look like? So we'll add the input data to cancel, and we will try debugging the cancel request. So we'll go down to here. So this is where the cancel order request is handled. It sets up a order cancel rejection. And we know why this is failing, but let's see how easy it is to debug it. So I press debug. And so let's have a look at this. So we've got cancel order request comes in. It's a bit hard to read. Yes?
Just had a message. They can't see the assert results when IDEA opens a window from the link.
Okay. Share. Thank you for that point. Hopefully this will look a bit better. All right, so I'll run the previous test again. But hopefully you can see that. You can see the pop-up showing that this is the cancel request. You can see that the account is being set on the way in, but we can also see that the result going out, the account hasn't been set. You can also see it as an ordinary Java object, because we're dealing with, these are plain Java objects in reality. So there's not a lot of magic going on here. We're dealing with ordinary objects that are easy to debug and easy to see what's going on. Now, what you can see, for example, is that the sender, the symbol, and the target and time are actually, in reality, they're longs. So that's where using the renderer can be useful to figure out what's going on. So, all right. Before I make the code change, I'll show you what the comparison looks like, since that was missing. Okay, so if we go to compare results, it's fairly easy to see what is going wrong. So it expected, well, I haven't updated the expected, so it wasn't expecting an account at all. And the actual account is coming through as null. So let's fix the code so that it's copying the account. Run it again. So one of the key things about this programming approach is how quickly you can iteratively develop these components. We're not having to start up a broker, or there are no brokers in this test. We're not having to start up some server. We're not, there's a lot of things we're not doing, just to keep things really simple, focus only on the business logic and do what it needs to do. We're not worrying very much about the details of the infrastructure at all. That means it can be run very quickly. So the very first test to fire up takes a little bit of time, but now if I run the tests, but when you've got multiple tests, they don't really add very much. So you can see the very first test, you had to fire up the code, took about 1.4 seconds, but The second test only took 15 milliseconds. And for a lot of our tests, they're in the order of 20 to 50 milliseconds, which means you can literally run hundreds of tests in a matter of seconds. And by making that very short, it means you can do it a lot more often. You can just make a change, run through all of your tests again. You have to wait a few seconds, and then you get a result. The faster that is, the more often you will do it, the quicker you get the feedback, the quicker you realize that either a test needs to be updated or you've broken something and you need to fix it. It speeds up the whole development lifecycle to have the tests run very quickly, very easy to develop and restart. This is using IntelliJ Community Edition. So it runs in a fairly simple browser very easily. And as you can see, all the tests now pass. So if you're going back to the, so in the presentation, it actually talks about everything I just covered, just some screenshots. In this case, I changed the order type. You can quickly see that that's what is different. And before I go into the questions, I'll just highlight what the next sessions are going to be about. We're going to be looking much more into the testing and benchmarking of these low latency microservices. How do we benchmark it and what sort of results do we get? Then we've got a session on visualizing the performance. So what is one of the ways of going about visualizing the latency hops between services? So you can see how much delay each service is adding and how much delay is there between services as well. And towards the end of, then the next session will be about low latency distributed transactions, how to have transactions across machines for high availability that can also support both very high throughput as well as very tight latency constraints. And now open up to questions. I think, Andrew, you might need to ask me what you...
Yeah, perhaps. So if anybody has any questions, you can either use the chat or the Q&A or even raise your hand and I'll open up the line for you. So anybody want any questions, please? I'm not seeing any. If somebody was to ask you a question, Peter, what question would you want them to ask you?
So what are some of the common mistakes people make when they're trying to write low latency benchmarking? So I could talk a little bit about that. Sure. So one of the most common mistakes I see is people using constructs that are more expensive and slower than the thing they're trying to test. So they might try to time something quite short, use nanotime to do it, or use sort of data object or something, and then sort of have some print statement before and after. And the thing is that the print statement itself is both single-threaded and often much, much more expensive than the thing it's trying to benchmark. And so that significantly skews the results. Another very common mistake is to not check that the code is warmed up. So the JVM often doesn't compile the code until it's been called at least 10,000 times. So if you just benchmark the very first run or the first 10 runs and average them, that is correct, at least for the first 10 runs, but it's not necessarily the best result you can get. So if you really want to focus on what is the best outcome, you want to run a realistic data set more than 10,000 times. You may well ignore the first 10,000 and then report maybe the next 100,000 after that. And also look at a latency distribution. No, don't just look at an average and a standard deviation, because it's literally not a normal distribution. It's not normal. It's very skewed. You get latency distributions that are a very odd shape, not a bell curve in any sense. So things like standard deviation are meaningless.
Okay. We've got a couple of questions coming in now. So there's one question regarding exceptions. Do we need exceptions in low latency applications? I doubt that exceptions may produce redundant characters or string garbage.
Yes. So yes, that's good. You've got exceptions in error handling in general. So yes, you need to be able to handle exceptions unless you're going to write a bug-free code, which is obviously a good ambition, but realistically, you're going to get exceptions. However, I'm very much of the view that exceptions should be exceptional. They should be very rare. Writing a benchmark, for example, which is synthetic. It's a known data set. You've got complete control over exactly what it's doing. You shouldn't, at least for that ideal case, be producing any exceptions at all. Obviously, in the real world, you will run into situations where exceptions are produced. Probably the most common exception that occurs in our code when it's running is failure to connect exceptions. So it's one of those exceptions you cannot eliminate. So whenever a client is connecting or it disconnects ungracefully on the server, you will get an exception thrown, an IO exception of some kind thrown. So it's not possible to eliminate that, but you can. You can say that shouldn't be happening very often, and when it does happen, you throttle it so that it doesn't happen too often. And there is a possibility that eventually, if you produce enough exceptions and you try reconnecting long enough, you will fill up your Eden space and trigger a GC. But it's not necessarily the end of the world. You probably should have, you may have been in what is an error state for hours before that actually happens. So yes, you want exceptions to be rare, but you shouldn't assume that you can eliminate them entirely. That being said, the CPU cost of an exception, if it's cold enough, can be surprisingly low. You can get exceptions down to adding about a microsecond, because what the JVM does is that once an exception is called enough times, it stops adding a stack trace to it, which makes it harder to trace, of course, but it makes it relatively, it's not as expensive. So then there's the question of error handling. So a traditional way of handling errors and possibly exceptions is just to log them. As you can see in our example, all the output goes out the output interface. So we try to log as little as possible. So the things that we do log are when there's a really critical error and you can't send it to the output, or you just want to let the user know that the service has started up. So you've got some startup information, maybe a dump of the configuration at that time, so that you can sort of check that the service is behaving correctly. But for the most part, you don't want to be logging anything at all, because the logging is one of the most expensive things that a lot of systems have, and they often realize that they have to turn off debug logging to get performance. But then when you turn off debug logging, often you lose a lot of the information that would have been useful. So instead, we just log everything via a queue. So send it out to a queue. You can then have another process reading that queue and dumping it to a normal text file if that's what you really want. That can even be done on another machine, so that you're not impacting your core system. But you do need to have error handling, and that error handling can record exceptions. It can record normal errors, but you want to make them as much as possible to be able to be handled automatically. So when an exception or error occurs, you can pass that back to a client or a GUI or some monitoring system, and all of that is machine parsable because it was all written in a format that's machine readable right from the start. Whereas if you write it to a log, you're not checking when you write the log that you're writing enough information. You may have missed something. You may not be entirely complete. It may be also redundant. So often when people log things, they'll log some sort of error in one place, then throw the exception up, and then end up logging it again somewhere else. So if you're not handling it carefully, you can end up with both it's both verbose as well as not complete. So neither of which is ideal.
Okay. Next one. Somebody said, can you expand on the Chronicle Q map configuration used in the demo?
Okay, so in this case, there is no map, so that makes it quite simple. Where it would be used, it would be in the order management. But since I'm just rejecting every order, I'm not really using a map. But in a more realistic example, there would be a map here, which could be Chronicle Map. It doesn't have to be. It depends on what your plan is in terms of restarting the service. But if it was a Chronicle Map, it would be just a map sitting in here. You would use it to store the orders so that you could handle the state of each order and all of its changes, and clear out the map, or do a remove from the map when you no longer want to record information about an order. So from Chronicle Map's point of view, configuring a Chronicle Map is a little bit tricky in certain situations to create the map. But once it's created, it's very simple because it's just a concurrent map. It's got some extension methods, but for the most part, you can just treat it like a concurrent map. Where it gets a little bit tricky is trying to find the optimal tuning. And my answer to that is usually, well, don't try and optimize it too much unless you're trying to write a benchmark and you want to get the very best result. Instead, I would just encourage people to give it a little bit of headroom. Just because it expects you to tell you how big the records are going to be and how many records. If you just make it, unless you've got a really large map, you can often just give it a bit more headroom, make the entries a bit more than necessary, and it will perform pretty well and not waste very much space. Now, in terms of the queue, so what's interesting from this test point of view is that we can test the business logic without the infrastructure being involved. So a queue is not actually used directly in this example. It's implied. We can create a harness which reads entries from a queue and then writes the results to another queue. However, in this example, that's not actually necessary to test the business logic, because the business logic should function correctly whether the queue is there or not. It's just in this case, it's just one method in, produces one method call out, and in fact, you don't even need the test harness. You can literally do that from Java, directly from Java. The configuration of the queue itself, what would I expect it to be? In this case, it would probably be either a daily rolling or an hourly rolling queue. Queue doesn't require you to configure what data is going to be in it or how large the data is going to be. Is largely unimportant. So queue is a little bit easier to configure, but in terms of use, we very much encourage using this method call model where when it's read, that turns into a method call, and when it's written, it's all essentially serializing method calls. And then you can now test your business logic and your infrastructure completely separately.
Okay. Next one. Do you have tests on GitHub that demonstrate Chronicle doing low latency ACID transactions?
Yes, that's the subject coming up.
Oh, good.
So the low latency distributed transactions. So in terms of ACID, we tend to, in terms of CAP, we tend to go for eventual consistency. This gives us the lowest latencies with what is for the client an acceptable loss of data. So that's the trade-off most of our clients are willing to make. That there could be a small amount of data loss, but they get the best possible latencies, and that's more important than the other way around. The reason they can do this is that traditionally banks were voice managed, so every transaction was actually done over the phone, or probably in writing before phones existed. So they still have those mechanisms, and they still have those mechanisms for correction as well. So should an order system fail, a client can ring up and say, look, I placed this order. I know you don't have a record for it, but believe me, this is an order that actually occurred. And in many cases, they can be surprisingly understanding when it comes to correcting those sorts of things manually, even when there could be hundreds of thousands of pounds at stake. And that's because reputation is very important. You don't want to either get a reputation for being difficult, but you also wouldn't want to get a reputation if it turned out that you were not telling the truth, because that's essentially the end of your career. So the fallback is then to something manual, and they've always got the capability to have manual intervention anyway. So as a result, a small loss maybe every couple of years is an acceptable trade-off for having very high performant latencies. But this is not true of all financial systems, and in particular, it's not true when the clients you're dealing with are retail rather than institutional clients. And for that, we've got a different approach which involves synchronous replication. And that allows you to have a redundant copy on a second or tertiary system to ensure that everything is recorded, and should you even lose a data center unrecoverably, you won't lose that information. So that's the approach we've taken. So give me a bit of a teaser as to what that looks like.
Right.
And
sorry,
go.
No, I was just going to ask you the next one, unless you wanted to continue teasing.
Go on.
Are there any features in the new JDKs, e.g. foreign memory access API, Graal VM, that we are looking at or planning on supporting, which could be helpful for performance elsewhere in a client's application?
Yeah, so there are a number of features where we've used Unsafe directly in Java 8. So there are a number of features that are in later versions that allow you to get the same kind of capabilities with pretty much the same performance, but do it in a way that's supported. So it's not supported in Java 8 directly, it just happens to work. And obviously the JVM providers don't like that because they don't see it as supportable. However, it's just a pragmatic decision. So in the newer versions, they've made it supportable. The problem is that it's only available in newer versions that banks don't use. So at a certain point when banks no longer need Java 8 support, we'll probably cut across. What we will also likely to do is perhaps maintain two versions for a while, where if you've got Java 11, for example, you can use the newer features. But if you're on Java 8, then that will still be performant. There's not a lot of imperative for us to switch, partly because most of our clients still use Java 8, but also because at best the performance will be the same, it's just be more supportable manner than it was, and slightly more secure as well. So if you're running in an insecure JVM, then that's another reason to use these newer features.
Okay. There's a couple more. Is it worth using base 85 for strings that are repeated through the system because they would get pulled slash cached?
Yes, so we do string pulling. So we have that already. So if you, when it deserializes a string, it implicitly pulls it. The performance, because of the pull we use, the performance is actually very similar to creating a new string, but you get a better memory footprint. However, for strings that could change quite often and reduce stress on this memory pool, we also have the option to use a long. With a string, you're still following a double dereference. So if you want to do a string comparison, you have to look up the string, and in the string you have to look up the array, and then in the array you have to look up each element of the string. So if two strings are equal, that can involve more than a dozen memory accesses, even for a short string. However, if you've got a long, then that's one memory access. You've got a long in each hand. You can compare the entire long as just as a straight comparison. So there's some efficiency benefits to using a long over a string. However, it's certainly not a requirement. And a lot of these optimization techniques, we have other optimization techniques such as using mutable data types, strings. Often clients look at it and they go, that's very cool, but we don't need it. We'd rather just keep things simple, and that's fine. And in fact, generally we encourage people to keep things simple. Just go for the easiest to use to start with, but know that should you need these optimizations in the future, you've got some idea as to what sort of benefit they would have, and you can decide on the trade-offs. And the optimization for these fields, for example, is on a per field basis. If I were to change a string to a long, none of the tests have to change because they're all using strings and they're doing implicit conversions. So all I have to do is change the type. I'd have to change some of the code, obviously, because now it's going to be a long instead of a string, but you minimize the impact, and it's isolated to just that field. If I want to change how a particular DTO is optimized, again, I can optimize that DTO. We don't have to change everything else. That's because it's very common for a trading system to have a small number of DTOs which are used a lot and are very performance sensitive. But the majority and have a large number of DTOs that are relatively complex but relatively rare. So, for example, configuration is often very complex. You've got some sort of complex data structure that, as a result, tends to evolve quite quickly. So you want to be able to handle schema changes very readily. However, it doesn't need to be performant. It shouldn't be going through the system many times per second, for example. It should basically go through when it changes and then be cached. So as a result, we're of the view there isn't a one-size-fits-all. You want to start with what is the simplest, and then once you see the system running, you can tune particular examples to be more performant, and with the understanding that that means that their manageability and maintainability is there's some sort of compromise that you'll have to make as a result.
Okay. Couple more. How large do we size the Eden space to avoid minor collections in a day?
For a system, depending on how the system's been tuned, I would start when I first built a system that did this. I made the Eden space 8 gig, and it took 24 hours to fill up on a busy day. Later, I made the Eden size 24 gig. Seemed to be a good size, but that's before we started using off-heap memory in a serious way. In this example, you could run through, because everything is reused, right? So all the input DTOs and all the output DTOs are reused. You could run through millions of events and produce almost no garbage whatsoever. So a lot of our clients once they put everything off heap, you know, with all the maps and all the queues and all the events, we're looking at only a few gigabytes of heap. And in fact, if you've got a system that's kind of limited in memory, you actually want to have smaller heap sizes so that the system can cache more of the off-heap data in memory. If you give it a really large heap, then you've got less space to cache the queues and the maps, which are all off-heap. So more recently, I would say that the trend is towards heaps or Eden space, mostly Eden space. In fact, between 1 and 4 gigabytes, and old gen being smaller than the Eden space as a result, because there really isn't a lot being retained that's not either off heap or just temporary objects.
Okay. Do we plan any fast parser to be released?
Do we plan any
Fast, F-A-S-T.
fast parsers?
Mm.
Yes, so our fix engine at the moment doesn't support fast. We have had the occasional inquiry about that, but not enough to make it worth developing one. Obviously, I'd be happy to support it, but we did not really had enough interest to justify it, I would say.
Fair enough. Well, that's, I mean, and Altan's asked, are we planning a presentation about our low latency messaging bus, which I think we will be doing at some point. Was that right?
Yeah, so we can look at this much more from the perspective of the queue itself and queue replication, which is the distribution of the queues. I think we should put down that as a topic, more low level look at queue.
Yeah, that's what I thought. Yeah. Okay. Oh, somebody's just come up with another one. Is it faster to look up an object given a long in a java.util.hashmap versus Chronicle Map?
Okay, so the problem with, so one of the benefits of a hash map is that you're not really looking up an object, you're looking up a reference to an object. So no matter how big or complex the object is, you're not doing very much work. The downside is that it has to have an object as a key. So if you've got a primitive long, you end up creating a wrapper just to do the lookup. There are other hash maps such as Trove and Colorbook which allow you to take the long as the key without creating a wrapper. So that can mitigate that. However, the lookup of Chronicle Map, where that can, the thing to consider there is that because it is off heap, it's not the actual object. It has to deserialize the object and it has to reserialize again to update it. So there is a way around this, which is to use a flyweight. So you're not deserializing the entire object and you can get comparable performance. But that can be quite restrictive because maintaining flyweights and making use of them isn't the way a lot of developers think. So in reality, most developers just use the object serialization that we have, and that adds a little bit of overhead, but it does have the benefit of having no garbage overhead. So not only does it not create a lot of in the temporary objects, it also does, when a GC occurs, it doesn't really matter how big your Chronicle maps are. It won't change the GC time.
Perfect. Well, I think that's about just perfect on time. So thank you everyone for joining. As Peter's mentioned, we will be doing another one on May the 14th, which is around the testing. So obviously we'll put the invites out again, meet me, and so you can register there. There'll also, this presentation and a recording will be available in our Chronicle Performance Engineering group, which is our closed user group on LinkedIn. So if you're not registered, feel free to register. Not only will you get content like this, Peter also sometimes posts some exclusive blogs on there, etc. So it's worthwhile registering. But yeah, thank you very much for everyone attending, and hopefully we'll see you in a couple of weeks. Thank you.
Thank you, everyone.
Thanks a lot.